Hello all, we are in the week 4. This is a lecture 1 of our week 4. So, let me know how to mitigate the effect of fading. I hope all of you must aware about what is fading. It's a noise in a wireless communication system, or we can say a multiplicative noise. So it's quite obvious that improving the BR performance helps us to mitigate the effects of fading. And at the same time, if we increase the diversity order, we can improve the BR performance. Then my next question is how we can increase the diversity order. The answer is quite simple, by employing the more number of antennas, because as large the number of antennas, there will be large probabilities of getting more number of copies of the signal at the receiver. However, while employing large number of antennas, we also need a technique, a beamforming technique, which helps us to get the independent channels. Whereas this beamforming technique requires the information about the channel at the transmitter. Whereas it is not always possible to have a CSIT. In a practical scenario, it is not always possible that the channel information will be available at the transmitter. Hence, the new technique has been introduced, which is known as space-time block coding. It helps to attain the same diversity performance equivalent to the beamforming, while in the absence of the channel state information. In other words, we don't need channel state information at the transmitter, however, able to attain the same diversity order equivalent to beamforming by deploying space time flow code STBC. The STBC, or I can say linear STBC, is looks like this. This X is a STBC code matrix denoted as capital X. Is a combination of these terms xn bar an plus I xn tilde bn, where this x1 to xns denotes the set of symbols to be transmitted. An and Bn are fixed code metrics of dimension nt cross n, and ns are the total number of symbols transmitting over the n time interval. This capital N represents the n time interval, total time interval, and nt is the transmit antennas, and ns is the number of symbols. So it means we are transmitting ns number of symbols per time interval, which is equivalent to the rate, right? There are two categories of STBCs. One is orthogonal and second is non-orthogonal. Non-orthogonal is not into your syllabus, so we are going to discuss about the orthogonal STBCs. Whenever this condition happens, x into x Hermitian equals to n is 1 to ns mod of xn square into I, where I is an identity matrix, then we can say that X is an orthogonal spacetime block code. However, at the same time, AN and BN needs to be satisfy the following properties. An into An Hermitian should be identity. Bn into Bn Hermitian is also identity. An B P Hermitian is equals to B P A N Hermitian. Right? The n is from 1 to ns, and similarly p is from 1 to ns. Right? If A and Bn satisfy these properties, it is known as amicable orthogonal design. So let's understood the things with the help of an example, where x is given as this. The Name of this particular matrix is known as Alamoti STBC. Alamoti is the name of the person who developed this sort of matrix. Let's first check this x into x Hermitian. It looks like mod of x1 square plus mod of x2 square with the diagonal. So we can write it in this. There should be an I here. It should be I, right, with 2. Identity matrix of this 2, right? So in a vague manner, we can say that it is an orthogonal STBC. Later on, we will see about the amicable orthogonality of AN and BN, right? Let's talk about its data rate. How many numbers, how many symbols are there? X1 and X2. Then NS will be 2, right? So while calculating the rate, we need to consider this whole overall block because we are transmitting this block, right? The fading is static while transmitting this block. We are assuming it. This is known as block fading, right? So how many time intervals are there? 1 and 2. Then total time intervals are 2, right? What would be its rate? Its rate will be 1, right? Which is the maximum one we are getting, we are achieving through this sort of block code, right? Now let's see how to evaluate an and bn of this matrix. See, the each symbol has its real part and imaginary part. The input bit streams are modulated over MPSK or MQAM, right? For example, for m equals to 4, it will be 1 plus I, 1 minus I, minus 1 plus I, and minus 1 minus I, right? So it's like for 1 plus I, or I can rewrite it like this 1. So this would be my x1 bar, which is 1, and this would be my x1 tilde, right? So in general, this x1 is x1 bar plus iota x1 tilde, similarly x2. So substituting these terms in the x, right? Let's say it's an equation 1. And as far as linear STBC is concerned, its uh, expression is like this: an into xn bar plus iota xn tilde bn. For ns equals to 2, which is the case here, it would be a1 x1 bar iota this and this. Let's say this is an equation 2. I would like to mention here what is A1, what is A2, and what is B1 and B2 in terms of the symbols. A1 is the coefficient of the real part of x1, and A2 is the coefficient of the real part of x2. Similarly, B1 is the imaginary part of x1 and B2 is the imaginary part of x2, right? However, we have already seen the dimension. This AN and BN are the matrix of dimension nt into n, right? Where n is the total number of intervals and nt is the number of transmit antennas. So here an would be 2 cross 2 matrix and bn will be also 2 cross 2 matrix. This a1 2 cross 2, b1 2 cross 2, a2 2 cross 2, and b2 is also 2 cross 2. Okay. So let's see in another manner. This x1 is nothing but x1 bar plus iota x1 tilde, and x2 is x2 bar plus iota x2 tilde. Similarly, what would be x2 conjugate? If x2 is x2 bar plus iota x2 tilde, then what would be x2 conjugate? X2 conjugate would be x2 bar minus iota x2 tilde, the conjugate of this, right? Similarly, x1 conjugate would be x1 bar minus iota x1 tilde, and then multiply with minus, it becomes minus of x1 bar plus iota x1 tilde, right? As I already told you, what would be a1? It contains the real part of x1 or the coefficient of x1. So what would be the coefficient of x1 here? 1. Then put the first element of a1, 1, right? In this second element of this matrix, whether x any quantity of x1 here? No. Right? So we put it here 0, right? Similarly, no x1 here, 0. Here x1, yes, real part, yes, the coefficient of real part is minus 1, minus 1, right? So we put here minus 1. Similarly, a2 is the related to the x2, the real part of x2, right? Is there any x2? No, 0. x2, yes, real part x2, yes, the coefficient of x2 is 1, hence 1 here. x2, yes, x2, coefficient of x2 is 1 here, so 1 here. x2, no, no x2, 0 here. In a similar manner, we can easily calculate b1, which is the imaginary part of x1 or the coefficient of x1 tilde, right? So in the first part, x1 tilde is there, yes. Imaginary part, yes, the coefficient is 1, so we will put here 1. x1, no, 0. x2, and x1 is there, no, 0. Then x1, yes, x1 tilde, yes, the coefficient of x1 tilde is 1, 1. Similarly, b2 is there, 0, minus 1, 1, 0. Now let's see whether it is amicable orthogonal or not. a1 into a1 Hermitian is equals to I or not, or you can say that I2, identity matrix of order 2, right? And similarly with a2, yes, it is following that a1 into a1 Hermitian will be the identity matrix, right? So it's amicable orthogonal. Then we can say that X is a orthogonal matrix or orthogonal STBC because it satisfies the first property, x into x Hermitian is this, and then a1 into a1 Hermitian, b1 into b1 Hermitian, and a2 into a Hermitian. These are identity matrices, right? So if you substitute these values of a1, a2, b1 and b2 in equation 2, if you put these values up here, which is a matrix, a1 is a matrix, if you put this matrix here, a1, b1, a2, a2, and solve it, you will easily get this equation 1, right? Now what would be its diversity order? We will see the diversity order analysis later on while evaluating the beta rate. However, I would just like to give you the glimpse of it, uh, how the transmission scheme will take place for this particular block code. Consider 2 cross 1 system where we have a transmitter 1 and transmitter 2 and a single receiver. In the first time of instant, x1 would be transmit through a transmitter 1. You can say that this column, first time interval, right? And this is from the transmitter 1 and transmitter 2. Similarly, this is from transmitter 1 and this is from the transmitter 2. Fine. So if you go ahead here, you will find out that the total number of copies of x1 and the x2 would be 2 at the receiver, right? And the first instant, one copy of x1, and the second instant, another copy of x1. It doesn't matter, minus and this conjugate here. We will see the x1, as I told you, later on we will see what would be happen to this minus of x and conjugate. How we are saying that doesn't matter, right? Okay, so how many copies of each symbol we are receiving at the receiver? Two. Hence, we can say that the diversity order of this Alamoti STBC will be two, right? This is another example of a named as a diagonal code, which in which we are transmitting the symbols diagonally, named denoted as x1 and x2. It is given here, or we can assume here, like just for the convenience, that mod of x1 square is equals to mod of x2 square. It's a unitary constellation property. You don't need to bother about this right now. So try to find out or verify the things which is written here about the rate, about the orthogonality, and how to find out the an and bn. Try to find out by yourself, then see the answer, which is in good practice, and find out its diversity order as well, right? Using the transmission scheme, right? This is all for this lecture one. Thanks.